ELTN 132. We're in Unit 9, MSI Circuits, and this is a continuation from last week. And so I wanted to kind of go over just the whole, what I call the whole enchilada here, the whole big circuit. In the lab, this is broken into 3 sections. You've already completed section 1, hopefully with the 4040 and the 74151. And then it's broken into 2 more sections. And I want to go over each of these parts so you get a sense of what's going on. I know there's a lot going on here, and we haven't really talked about the specific devices. But so let's take a look at this, and hopefully this will help a little bit. Okay, so let's start with the first part here that you worked on this last week. The 555 oscillator is that little board that we're using. And I went over the details on how that works last week in the video. The LED here is simply a way to indicate, to make sure that the output is working, even though there's a little LED that flashes on the board. Now, one thing of note, on that board there's a little black and red switch, and you're going to need to use that from time to time in this lab to turn on and off the output. So just be aware that that's on there. And you want to set that for approximately 100 Hertz. I know that's kind of an eyeball thing. We'll talk a little bit about how that looks when we actually look at the rest of the circuit. So if you research the 4040 on the internet a little bit, you probably saw that it was defined or called a ripple counter. And what that is basically the pin 10 is a clock input. So we have, and that's always notated or often notated with this little kind of side triangle. That shows that that's a clock input. So the 555 oscillator is putting out square wave pulses to that clock input. And every time it receives a clock input, a transition from low to high to low, it sequences the outputs in binary. So hopefully you saw that when you ran the lab. The reset, if you had a positive input on this, would reset or clear it back to 0. That's something that we don't usually use here, so we just ended up grounding that input. So the 74151 is what is referred to as a data selector. And in this case, the output from any of these pins is routed to Y depending on the values of the select inputs A, B, and C. And so what's happening here is that if we looked at the output, every successive output going from Q1 all the way through Q10 is going to be divided by 2. So, for example, if we had 100 Hertz on the first output here, the next one would be 50, then 25, then 12.5 Hertz, and so on, and they keep getting divided down. The inputs are selected by the dip switch. So basically what this is allowing us to do is to change the output frequency on the Y pin based on the select inputs. You can think of it as a rotary switch in a way where as you're moving that switch, it's selecting a different input to be routed to the Y output. So that's the data selector. The next part is a counter, and this is a 4-bit counter. It counts from binary 0000 to 1111, and it's an up-down counter. Now we're only counting up, so we have the output from the 74151 going to the up input. The down clock input is disabled. And then we have a load and clear buttons down here. So the way this works is that whatever data is coming into A, B, C, and D can be preloaded into the counter when that happens when you press the load button. It's inverted because that's active low, and we can also clear the counter. So that basically allows us to count up or down to a specific value. So the next part that we're going to look at are the 7-segment display and the 7442. Oh, and I did want to mention, I'm sorry, on the 74193, there are also these output pins called carry out and borrow out. These are basically used to cascade to other devices. If we want to count, like instead of a 4-bit counter, we want to make an 8 or 16-bit counter. So the output of the counter are pins QA through QD. Q is often used as an output for counters. or for other clock devices. And all of those output pins are connected to 3 different devices. The first is a 7-segment display board, and that's going to show your count on the 7-segment display. Blanking is grounded, and the phase and load should be tied to 5 volts. I believe those are correct, so if something doesn't work, let me know on that. The blanking basically allows you to blank the data output regardless of what the inputs are. And that's used in what is called lead zero blanking, if you don't want to have a bunch of zeros in front of a number at the end. The phase can be used to select for a common anode or common cathode display, or even to connect to an LCD display. And the load can be used to clock or store data into the memory of the device that drives the LEDs, or the 7-segment display. Next one is a 7442. It is a decoder, 4 bits in, and in this case 10 bits out, 0 through 9. You'll notice the outputs have bubbles, which means the outputs are inverted. And so to wire this, the LED is kind of wired backwards from the way we usually do. Now you can use the bar LED, bar graph LED display that you used previously last week for some of this, and then tie 2 more LEDs on outputs 8 and 9. I'm sorry, I probably didn't supply enough LEDs for you to wire all of them, but if you did, you can use those. Now, if you happen to have 10 LEDs, you can wire those all up and then use the bar LED for the last part. So the last part here is basically we're just taking those 4 data pins that are counting in binary and outputting them to LEDs. So the output display is going to show 3 things. It's going to show a 7-segment display of the count. It'll show an individual not binary, but an individual discrete output, lighting up 1 LED for those outputs. And finally, it'll show the count in binary. So hopefully that's enough to kind of give you an idea of the overall function of the circuit. The lab is kind of complex. Make sure you follow the instructions. But if you've gotten to this point so far, I think you'll be in pretty good shape. If you have questions, feel free to email me.